Welcome to the third part of our interpolation tutorial, or tutorial 2. We're going to begin with kriging. And kriging is a bit different from IDW interpolation, where there's a constant rate of decay, or the importance of each point reduced at a constant level as you got further away from our observation that we were interested in predicting. Now, kriging allows us to specify that relationship to distance and the importance of values as they get further away using different models. And so instead of just saying, as you get away, you'll decrease importance by x or x squared, you can vary that relationship. So let's begin by adding some familiar libraries, or loading some familiar libraries. The dataset we're going to be working with in this tutorial is the Muse dataset, which is a river in Europe, and we have some observations about heavy metal concentration in the topsoil. We have other variables about landscape and general soil characteristics stored with it as well. So load the data set itself, and then we can use the glimpse function to take a quick look at it. And we can see that we have an X and Y coordinate values, and then we have lead, copper, cadmium, zinc, elevation. We are going to be interested in this lead variable. The data itself is a data frame right now. And with data frames, we know we can work very easily with ggplot. Let's create a map of our data using ggplot. So we call our ggplot function and direct it to the data. Add the point geometry. For our aesthetics, we just set x to our x coordinate and y to our y coordinate. We'll vary the size of the points based on the lead concentration. We'll use the color brown, and we'll add a little transparency to our points. Add a title, run this, and here is a map of our observations. Now, what you may have noticed is this last function, coord underscore fixed, or coordinates fixed. And what it's doing is it's making sure that a distance across our x-axis is equal to the change in that distance on our y-axis. If I remove it, it will make a little bit more sense. By default, ggplot is showing our map with this structure, and it's in this landscape, and it shows the points spread out, but it's not really proper for our projected coordinate system. So this is actually representing our projected coordinate system. So if you take this distance, which is 1,000 units, 1,000 meters, it is the same as this 1,000 meters now. If we excluded that, we can see that this 1,000 meters is a lot wider than this 1,000 meters is tall. So you're making maps with ggplot through this set of functions. Just set the coordinates to fixed. Okay. Now, since we had a data frame, to work with our gstat package, where our kriging function is, we actually need to create a spatial points data frame to work with that. It's actually pretty quick to do. We use this function called coordinates, and we're going to give it the variable names that we want to use for our coordinates, or sorry, the names of the vectors that we want to use for our coordinates. So if we do this, we'll run this, and if we now look at the class of that, we see it's a spatial points data frame. If you run this function without adding this on a spatial points data frame, it gives you the coordinates here. but it allows us to set the coordinates for a data frame, and it automatically creates a spatial points data frame. Now, one thing we haven't looked at is bounding boxes. And all of our spatial data frames, points, polygons, lines, have a bounding box stored. But we can access the bounding box. We can use the bbox function, and it gives us the x and y min and max to create a bounding box, essentially a rectangle encapsulating all of our points. And this will be handy later on when we try to define our area that we want to interpolate. Now, with IDW interpolation, at this point we could have simply interpolated the values. There is another step in kriging, which is to fit a variogram model, which is essentially the way that the weightings of distance are going to be applied. So the first thing we need to think about when kriging as well is that are our variables normally distributed? And with this lead data set, they're not. So as with most pollution data, it looks to be log normal. So we'll take the log, and when we look at a histogram, it's better. It's not perfect, but for this tutorial we will move forward. So our variogram that we will need to fit is a model, or essentially a function. First, what we need to do is looking at our empirical data or our observed data, what does the relationship look like between semivariance and distance? So we will fit a sample variogram to our data. And so we need to give it a formula saying that we want to use the log value of lead that we created up here. Here we created the log of this value, stored it here. Actually, let's just go back to that for a second. If we were working with a data frame object, we could use something like mutate from the tidyverse. In this case, though, we can't do that on our spatial points data frame. It doesn't allow for that. So what we do is we find our variable, our spatial points data frame. We access the data portion of it, the data frame portion. We assign a new variable name, which is the log of lead, and then we create our variable, or a vector of values, which is taking the log of the existing lead values, and we assign them to this new variable that we create in the data portion. So now let's fit this sample variogram, and we can look at this here. So here in our sample variogram, we have semivariance on the y-axis, and then we have distance. And these distances are binned, okay? You can't see the lines of the bin, but they're there, and there's 14 bins by default in the gstat package. And what we're trying to do is look at kind of how the form of this semivariance changes across distance. We want to then understand what type of model we could fit that might fit well to how this varies. Now, since we're just beginning to work with kriging, we're not as familiar with the variogram models. And there's actually a large number of models available. So what we can do is call the show.vgms function, and it will show us the different variograms. And so we're trying to look for one of these. This is a linear variogram here. We have a log, power, circle, we have lots, exponent, spherical. If we look at the spherical one here, seems to kind of match pretty well with how semivariance changes relative to distance. And then there's this point probably around here where semivariance flattens out. And this is the point at which, points at distances greater than that aren't really contributing to our kriging any longer. The spatial correlation beyond, say, about 950 meters, which is our range, it's more similar to just random noise. So what we need to do is select one of these variograms, and we need to estimate its parameters. Okay, so it has a few parameters, such as a nugget, range, and sill, and we need to estimate those to use in our kriging. And thankfully, we don't have to estimate those manually. There is a function called fitVariogram in the GStat package. So you need to give it your sample variogram, which we saved as lead.vgm, and then you need to tell it which variogram model you want to have it fit with. And it's going to do an automated fitting process for us. So we can run that. It's now fit the variogram. Okay. And let's just plot this. So we'll plot our variogram model and our sample variogram, which are our points. Okay. And let's just talk quickly about what's going on here. So again, semivariance along the y, distance along the x. Okay. So we have a few points. We have the nugget, which is where our our variogram crosses the y-axis, and in this case it looks to be about 0.5. We have the sill, which is the semivariance value at which the semivariance flattens out, which here is probably about 0.55. And then we have the range, which is the distance at which that flattening out begins, which if I were to take a guess is probably around 950. Now, of course, we don't have to guess. If we call our object or our variogram model, we can see that the nugget is 0.05, that the sill is 0.51, and that the range is 965. What we may want to do, we're not going to do it here, but what you'd want to do at this point is potentially test out different models, so that instead of that spherical one, try out other ones that may fit. And looking at that, you can then cross-validate those models to choose which semivariogram is probably best for your model. But we won't do that right now. What we're going to do is look at the process that we have to calculate out or interpolate values. And in this scenario, unlike the IDW where you're provided a set of points, what we want to do is interpolate values along a grid. Okay. Now, we're talking about interpolation. So what we want to do is make sure that all of the points that we are estimating are within the boundary of our observed locations. The way we create this boundary, or what this boundary is called, is a convex hull. So it's a polygon that goes around all of the points. Okay, and it's a little tricky to create in R, so we'll just walk through how we do that. So we have a function called chull, and what it does is, given a set of coordinates, it identifies the row IDs of the coordinates that make up the convex hull. So let's just take a look at what that means. So these are the coordinate IDs that make up that convex hull. Okay, so row 155, 146, 147, 148, 92, 61. Okay, so that's just the row IDs for our Muse observations. We then need to subset out the points that make up the convex hull, and we want to create a polygon from those points. But we don't want the other points that fall within the polygon, which is a little tricky working with a spatial points data frame, because we can't use something like slice, which is very easy. What we need to do is the square bracket subsetting. Okay, and how we do this is given our coordinates. So just to take a look at those, given these coordinates, we want to subset based on rows. So in the square brackets, it looks like this before we enter anything. So we have row and column subsetting. Here we're only interested in the rows. And we want the rows based on these point IDs. So we want row 155, 146, 147, and so on. And then we're going to take this output and we're just going to pipe it into a data frame. Okay. And here we are. So here are the points that make up our convex hull. And we now need to change this into a polygon. So this is also a bit tricky. So what we need to do is get a matrix of the coordinates. Okay. And we do this by using the coordinates function that we learned about earlier and calling it on those points, which gives us CRDS. So here's our matrix. So it's not a data frame, it's actually a matrix. It looks very similar. And now from our matrix, we can use the polygon function in the SP package. And you do note you probably have to call the SP package here because there's a number of functions called polygon, and we need to make sure that we are getting the right one. And if we give it the coordinates matrix, we can create the poly. And here we have an object of class poly. We don't need to move on from there. And then we need to create another two things. We need to give it an ID. And so we'll store an ID called minimum boundary. And then we have to store the polygons in a list of polys where we then set the ID. Okay, so this is a little tricky, but just follow along with the code. Sorry, make sure to run them in order. And now we can put that information into our spatial polygons. And again, we need to make sure that we're calling it with list surrounding what we created there. And unfortunately, it's a bit of a pain, but this is because we could have a list of multiple polygons. In our scenario, we only have one polygon, so it seems like a lot of work. But if you had multiple polygons to create a spatial polygons data frame, it would make sense. And here we now have our polygon. Okay, so just to go back over that, what we did is we took the coordinates of our points that made up our convex hull. We then created a polygon object, which is from the SP library. We gave it an ID, and we created a list of those polygons with the ID. And for us, our list is only one. And from there, we put it into the spatial polygons function within a list, and it allowed us to then create a spatial polygons data frame. And we can see this if we go class SPLS. Oh, there, spatial polygons. And it's not a spatial polygons data frame, it's just spatial polygons. We don't need a data frame because there's no data, no attributes associated with that. So now that we have a boundary, we need to create the regular grid of points. And so what we can do is use the makeGrid function. We give it an object that shares the boundary. So here we'll use the SPLS that we just created, and we give it a cell size. And we give it a cell size of 100 meters. So we want a point every 100 meters. If we look at that, it's a data frame. So let's just look at the structure quickly as well. We can see x1, which is the x coordinate, and then x2 is the y coordinate. Unfortunately, this makeGrid has this funny naming for the x and y coordinates. So we can take x1 and x2 and make that a spatial points object. And now we can see if we plot that, we have a point at every location, but they're not within that polygon boundary. So now we need to do the next step, which is to select out these points in our grid that are within the convex hull. And we do that using the function over that's within the SP package. So you give it our points, and then we give it the polygon that is our boundary, and it creates this object where for each point it says NA if it's not within the boundary, or a 1 if it is within the boundary. From there, we can select the points that are not NA using the isNA function, but by first putting the exclamation mark in front of it saying we don't want to select the ones that isNA is true. So we use this square bracket subsetting again. So what we do is we give our grid in poly, that object that we created, which is NAs and 1s. We say, is it an NA, which would return true or false. And true is when it is an NA. So we actually want to select when it's not true. So we use the exclamation mark and we put this all on the left side of the comma, indicating that we want to select out rows or observations. Once we do this, we can then plot it, and now we have our points that we can interpolate to that are within the polygon boundary. So how do we predict new points using kriging? We use the Krig function. We give it our formula, same formula as we are using in IDW. Give it our observed data. Give it our prediction locations. And then we need to specify the model, the variogram model that we created. Once we do that, we can run that. It's going to let us know that it was using ordinary kriging. Okay, so let's look at what our predictions are. And again, just like IDW, var1.pred is where our predictions are stored. So there's our predictions. We see our highest values on the outside, our lowest values on the inside. And remember, these are the log of values. So what we could do apparently it won't let us do that. What we could do is create within this object the untransformed values by raising them to the exponent. So here we've plotted the kriging values. Unlike IDW, we also get a variance estimate with each one, which you can kind of think of the estimation error. And we can plot that using var1.var. And really all this is a map of how close the nearest point is to that point. And where points are nearer, we're going to assume that the error is lower. We can just take a look at this object, just see the structure of it. So it has a data portion, which our data frame stores our predicted values and our variance. And then we have the other parts of a spatial points data frame. Here we do our cross-validation very much the same as before. The only difference is that we need to introduce which model we will be using for the cross-validation. And remember, we do not include the prediction locations when we're doing cross-validation. So we'll run that. It's taking some time because we have many more observations. And we can access our vector of residuals. And from here, you could calculate the root mean square error, for example. So that ends it for our tutorial here for number 2 based on interpolation.